Okay, so hi everyone, my name is Evelyn and I work with the EC Student Affairs Office, and I'm going to show you a video of the lab tour, and then after that, Professor Atanasov will take over. So, and let me know if you guys can hear everything.
Yeah, we can hear.
Okay.
The Existential Robotics Laboratory is part of the Conceptual Robotics Institute at the University of California, San Diego. Directed by Dr. Nikolai Atanasov, the lab's goal is to develop robots that have generalization abilities
Can't hear anymore.
only on onboard
Sorry.
sensing, computation, and control. The lab's research focuses on multimodal environment representations, autonomous navigation, active information acquisition, and distributed intelligence. While working on developing new algorithms to handle these challenges, it is also important to validate them in real environments with hardware platforms. Enabling these capabilities will impact the safety, resilience, efficiency, and versatility of autonomous robot systems and their utility in transportation, disaster response, environmental monitoring, agriculture, mining, construction, and security. This work area is for hardware development and robot repair. It is equipped with tools and components to assemble quad-rotor and wheeled robots using sensors, actuators, computers, and communication devices. These are several quad-rotor and race car robots currently in development. They have different sensor configurations and have different capabilities customized for the lab's needs. Here are the two main robot platforms that the Existential Robotics Laboratory work with: race car and quad-rotor. The robots are equipped with different sensors, including RGB or depth cameras, inertial measurement units, LiDAR and GPS, and various computing platforms such as Raspberry Pi, Intel NUC, and NVIDIA Jetson TX2 and Xavier. The lab also has several commercial drones from DJI, Intel, and local San Diego companies that are ready to fly. These hardware options allow for testing of the lab's autonomy algorithms on the robots either individually or collectively as a team. As a lab focused on robotics, the team designs and builds some of the components, such as camera mounts, propeller guards, and visual inertia sensors using 3D printing and laser cutting technologies. For more information, please visit erl.ucsd.edu.
Okay,
Evelyn, thank you so much.
no problem.
So
Okay.
this was a quick video overview of our lab, just so you have a sense of what it looks like physically as well, since you can only visit through Zoom for now. And I think maybe the most useful part of this session is that you guys ask questions and anything you're interested in. I also invited some of my PhD students and postdocs are on the call here, so you can chat with them, connect with them, ask them personal questions if you want. And maybe while you're thinking of questions, I can give you a quick overview of some of the actual research that we do, and then we can open it up to questions. So yeah, I'll just take a couple of minutes to give you an overview of the work we do. Evelyn, is it okay if I share my screen now? Yeah, all right. Let's see. So yeah, gonna keep it short so we have time for questions. So yeah, at a high level, we work on robotics, and we employ ideas from control theory and machine learning as well. And we're mainly interested in 4 problems. One is, how do we model the environment around the robot? The second one is, how do robots navigate autonomously? So this involves planning trajectories, executing them, making sure that the robot stays safe. A third area, which we're very curious about, is active information gathering. So this is the problem of exploring your environment autonomously. So kind of like humans and animals, when we put them in an unknown space, they like to peek around and learn about their surroundings. We're aiming to achieve the same behavior in robots. And finally, we look at multi-robot teams. So how can we do collaboration among robot groups? So here's some more details about these 4 areas I mentioned. So in the first problem, we look specifically at the localization and mapping problem, also known as SLAM. So we're interested in metric and semantic SLAM. So metric refers to estimating positions, orientations, poses, shapes of objects and surfaces in the environment, while semantic refers to identifying what is the meaning of things we're seeing, so recognizing different objects and classifying different surfaces and so on. So we're interested also in potentially having moving objects and building these object level maps or surface level maps in real time. So a lot of our focus is on being able to do this on board the robot without depending on external infrastructure. So we think about how to do things efficiently and on board. Kind of quick overview about the second area. We look at motion planning and generating dynamically feasible trajectories for these robots you saw earlier, like cars and flying robots. How do we guarantee not only that the trajectory is collision free, but also that it's actually executable by the robot? Is the velocity reasonable? Is the acceleration reasonable? Can your robot actually turn at the angle that you're proposing? How do we guarantee safety as well if there are obstacles or moving obstacles? Third area we work on is information gathering. As I mentioned earlier, here the problem is kind of to explore an unknown environment. So we look at algorithms which model uncertainty in the maps and ways to plan trajectories for the robots that minimize uncertainty. So we're interested in things like what motions of the robot will determine what camera positions and orientations, and how would these views of the environment reduce the uncertainty of our current model, or what extra information will this provide about our estimation task. And then finally, we're very interested in doing this with teams of robots. So we are thinking of things like, how do we do distributed estimation in a robot team? So what information should robots exchange among each other? And also, how do we do distributed planning and control? So how should the robots decide where to go if they have a common task? And how should they collaborate with others in the team, so that not everyone kind of goes in the same direction, and then the robots can achieve the task efficiently. So some applications of this work are basically anything that has to do with robot autonomy. So transportation, delivery, security and surveillance, environmental monitoring, agriculture. So we have projects in various particular applications. But again, the main focus of our lab is on the algorithms and theory. So how do we develop new ideas related to the 4 problem areas that I described? How do we develop algorithms, and then we validate them on actual road systems? Okay, so I'll stop talking now, and I'll be very happy to take questions. Yeah, because I think that's the most valuable, or we could discuss anything you guys want.
Thanks for the presentation. So I saw some nice hardware, and also you talked a bit about the research areas you're investigating, but what kind of a blend of it is there between the two? Like, do PhD students mostly focus on one area, or what percentage of their time do they spend on each?
Yeah, great question. So initially, when students are starting out, I think they need to learn a bit about both. So like have a little bit of experience with the more of the theoretical side, and have a bit of experience with actually programming in ROS and C++ and hardware on the robots. As time goes on, so I'm thinking here the first or second year, you want to get a sense of what the different options are. But as time goes on, I usually let students decide. So at least in my lab, it's very much interest driven by the students. So if someone is excited about hardware, has a cool idea, wants to develop that sounds great. If someone has a key idea on theory, and wants to prove a theorem about sensing or planning, that's also great. So yeah, overall, I let the interests dictate.
Can I ask a question?
Yeah, go for it.
So when you talk about you guys mainly do algorithms, are these like image processing or vehicle to vehicle communication, or like which main group do you guys focus in within robotics?
Yeah, very good question as well. So we are focused not on communication. So we're focused on the three areas I mentioned: robotics, control theory, machine learning, maybe some computer vision. But when I say yes, robotics is very general. So we do not do. So maybe an easier way to answer is things we do not work on. So we do not work on materials and hardware development. We do build some robots from components, but we do not do kind of extensive development on coming up with a new robot body or a new robot sensor or something like this. We do use communication, but again, we do not develop communication algorithms per se, or coming up with a new radio, or thinking about bandwidth and things like that. So we kind of use existing components for these things. So I'd say the main areas we work on are on the perception side. We look at things like object detection, position, shape estimation. We also look at probabilistic algorithms for estimation. So how do you track the position of the robot over time? How do you localize objects or reconstruct surfaces in the environment? And then we look at algorithms for optimization. So given these models of the environment, how do you state your robot's task as an optimization problem, and how do you optimize things like the robot trajectory, the robot's orientation over time. So we look at things like optimal control, reinforcement learning, and applications of this to real robots. I hope this was relatively clear. If you guys are, feel free to ask questions in the chat also. If you're shy to speak up, that's fine too. And if you don't have any questions, we could also share a few other things from some of my students could present a bit.
So, hi, Professor. Can you hear me?
Yeah, I can hear.
Oh, thank you for introduction. I've got one question. That I know that a lot of labs in the world are doing like the similar things with your lab. So what do you think is the biggest difference between your labs and other labs?
Yeah, that's a great question. So I wouldn't say a lot of labs, but there is a good number of labs. So maybe like every school maybe has a lab that works on, or at least several that work on autonomous robots. I would say kind of the unique, and again, I wouldn't say we're the only lab that does this, but one unique feature for our lab is that we have a fairly theoretical approach to robotics. So I've seen kind of a big disconnect between a lot of people who work on robotics have a very applied focus. So they're focused a lot on experiments and making cool videos, and spend a lot of time actually out in the field doing real experiments. While at the other extreme, we have people that work on control theory, that they develop a lot of interesting results in math, but oftentimes they don't get connected to actually what is going on in the real system, and questions like, how do things actually happen in real time? How do you actually represent things like position, orientation, velocity, mass, inertia? So things that actually become relevant when you try to implement a theoretical algorithm. So I would say our kind of unique part is that we think about the theory and how it translates all the way down to the physical robot system. Yeah, again, I think maybe there are other labs that do that, but that's our strength.
Sure, thanks, Professor.
Yeah, if while you guys are thinking about questions, maybe we can have some of my students also mention a bit about their work. That could be useful. If anyone wants to volunteer, I know Shan and Arash, you guys prepared some slides, so if you want to volunteer, well, and then if you have a question in the meantime, feel free to interrupt as well. There's no schedule.
Yeah, I can start. So my name is Moshan. I'm a PhD student in ERL. It seems like I'm not able to share my screen. So can I have the authorization to share my slides? Okay.
I
All
made
right,
you
so now-
co-host.
Yeah, now I can share my slides. So I will present our recent work on visual inertial odometry. And the title is ArcVal, Object Residual Constraint Visual Inertial Odometry. So the reason we want to propose, so the motivation behind this work is that we have witnessed different trends in two very different fields. First is in the traditional SLAM and the VIO. So the previous works are able to reconstruct very accurate geometric structure of the scene and also localize the robot pose. On the other hand, in the deep learning field, there's a lot of progress on the object detection and segmentation, but currently there's very little connection between the two fields. So we propose an approach that attempts to bridge the gap by utilizing the deep learning object detectors as a sensor in our model. And so we have, so for this measurement model, we have the object bounding box, we have the semantic key points on the objects. So those residues can be used to also optimize the object pose and also the camera pose as well. So based on this semantic kind of object sensor, we can formulate the problem in this way by constructing this cost function with all those semantic residues. And here's